Now divided chapter 30 into 3 parts. In part 1, which we're about to do, I show you how to use the algebraic method for finding power series solutions to differential equations. In part 2, I'll explain what ordinary and singular points are and how to find the interval of validity. And then in part 3, I'll show you how to use the Taylor series solution to differential equations. Now here is a general description of the algebraic method and what we're about to be taking a look at. And here is a step-by-step outline of the method that you might want to print off for your notebook. So I'll go through the steps to solve this differential equation using the algebraic method. So we're assuming here that the solution, since it's centered at 0, is going to look like this. We'll take the derivatives, first and second, and then substitute that into the original differential equation, and then do some manipulation. And then the next step is to write this as a sum of sums. And as you can see, this already is. So then we want to fix this where the exponents are all n's. We can do that on this first sum by increasing the n inside of the summation, which means decreasing it on the index. Then we want to make sure that the indices match. Well, again, they already match, so we don't have anything to do in this step. And then, like we did in the previous chapter, we want to combine these two together. Since the x's match and the indices match, we can write this as a single summation. Now, we want to solve this for a sub whatever it happens to be using the highest value. And so we'll take just the coefficient part, the thing in front of the x to the n, and solve that for that equal to 0. So the two choices are the a sub n plus 2 and the a sub n, the largest of which is the a sub n plus 2. And so we'll solve that for a sub n plus 2. Now this next one is going to take a little patience and practice. Here we're going to make a list for a's. I'll show you what we mean by the recursion form in just a moment. But let's just go ahead and list the values of n that we might be considering here. Just a few of them. We'll go from 0 to 5. And when n is 0, we come up with a sub 0 plus 2 equals negative a sub 0 over 0 plus 2 times 0 plus 1. So all we're doing is plugging a 0 in place of the n. Now first off, notice, I know I've already put this up there, but our first thing that we get when we start our indexing at 0 is a sub 2. Well, what does that mean about the a sub 0 and the a sub 1? Well, we know we're solving a second order differential equation, and it's going to have two constants. So we're assuming that the a sub 0 and the a sub 1 are our two constants. In other words, in the end, we need to come out with A0s and A1s, but not A2s and 3s and 4s and so on. So anyway, we'll continue on, do a little bit of simplifying on this, and then plug in a 1 for n, a little bit of simplifying on that. Plug in a 2 for n, and so on. Now, as I said originally, we want to come out with only an a sub 0 and an a sub 1, which is okay on the first two, but when you get down here to where n is a 2, notice that we come out here with an a sub 2. Well, this is where the term recursion comes in. If you look back up here, you notice that a sub 2 is equal to this. So we're going to take this a sub 2 and replace it with what we found back in the first step, and then simplify that. And then we'll do the same thing with the a sub 3. A sub 3, we say right here, and so we're going to replace this a sub 3 with what we had said earlier a sub 3 was, and simplify that. Now again, I'm going to go through this a little bit quicker, and we have this list. So then let's write our a sub n using the list that we've got. Now that's as far as we made it, so we'll just put the 3 dots at the end saying that, yeah, we know we stopped there, but it keeps on going like this. And then we'll do a little manipulating on that. And then, of course, what we would like to do is to see if we can match up these with known things. And sure enough, here are the functions for those two sums. Let's try that process one more time. This time we have a first order differential equation. And so we again assume that this is what our solution is going to look like since it's centered at 0. And we'll do just one derivative of that and then substitute. Now in this next step, we want to rewrite this so that we have a single sum here where all of this stuff is, and a sum where all of this stuff is. We want this to be a sum of sums, and so we need both of these to not have stuff on the front. Now again, we practiced this in chapter 29. We can put that on the inside of those. I'll kind of go through the explanation since all of that just popped up at once. We did this one times the sum, that's what we got here. We did this x squared times the sum, that's what we got here. And we're going to do this negative 2x times the sum. And so that's what we mean by writing it as a sum of sums. Now we've done this before. To make the exponents match, we need to add 1 here, which means subtract 1. We need to subtract 1 here, which means we need to add 1. And we need to subtract 1 here, which means we need to add 1. So we end up with this. Now, let me show you the end result. We'll start with the one over here on the left. we'll actually take the n equals 0, and 0 plus 1 times a to the 1 times x to the 0 would just be a sub 1, and we can write the remaining terms starting with an n equals 1. And so this is the first summation. Now the second summation, to make it start at n equals 1, notice here that if n is a 1, 1 minus 1 is a 0, so you don't even have a term. So we could actually start this at n equals 1 and have exactly the same series, because the first term, when n equals 1, is going to be a 0 anyway. So anyway, we can just change the 2 to a 1 on this one. And then the last one is already a 1. So now that they all match, we can put all the sums together. Now the a sub 1, again, is totally separate from all the sums, but we can combine the sums together. So now in this equation, we know that for the left-hand side to be equal to 0, the a sub 1 has to be a 0, and also the coefficient of x to the n has to be a 0. Now we want to solve the right-hand side for the highest exponent, or highest subscript of a, which in this case would be the a to the n plus 1. So let's do that. Then we want to make us a list. Now again, we'll just do a few of these. Here's n equals 0, n equals 1, n equals 2, and so on. Now, looking at this pattern, we notice that, again, because of the recursion, well, we're going to have, like, the next one would be a sub 6, which would be dependent on a sub 4, which comes out to be a 0, which means everything after this is going to be 0. So that means that our polynomial is going to look like this. Notice all the zeros out here will basically mean that we only have the two terms, a0 and a0x squared. So this one actually came out to be a finite polynomial. In other words, the solution to that differential equation is simply the quadratic function that you see here.